So variation. These are a little bit different type of problems, and they are word problems, but I don't think you're going to find them to be too bad. There are certain code words you have to pay attention to. So just to kind of introduce the idea, say you have a job where you're paid $10 an hour. What's the relationship like between the total you are being paid and the number of hours you work? Since you're getting $10 an hour, the more you work, the more you get paid. So as the number of hours you work increases, your pay is going to increase. Your total pay increases. But let's compare that to a different situation. See, you've got a second job and you've bid on it, and you've agreed to complete the job for a total of $100. What's the relationship between how much you ended up earning per hour and the total number of hours you took to complete the job? So if you managed to complete this job in 1 hour, you just got paid $100 an hour. Not bad. However, if it takes you 100 hours to complete the job, you're only getting paid $1 an hour. So you're getting paid a set amount to complete the entire job. So now, the total numbers of hours you worked, the more hours it takes you to complete the job, as that goes up, your pay per hour is going to decrease. So two very different relationships here, and we're going to explore those a little further. Okay, so problems involving direct variation. So for that first job, the amount you paid is 10 times the number of hours you worked because you're getting paid $10 an hour. So this is what we call direct variation. With direct variation, one variable is a constant multiple of another variable. So y equals kx. In this case, our pay, total pay, equals 10 times the hours we work. There's different words you're going to see, and again, this is kind of looking for the code words in each problem. We could describe direct variation by saying that P is directly proportional to S. The P varies directly with S. P varies directly as S. Any direct variation problem is going to end up having an equation, y equals some multiple of the second variable, which is our slope-intercept formula, y equals mx plus b, only the b is 0, it's going through the origin, and we're just calling m k for whatever reason, for addition. What we do call the k is the constant of variation, or the constant of proportionality, or the proportionality constant, depending on what algebra book you're reading. So, an example, suppose y varies directly to k. So we got our keyword there, that direct variation. And then we're given some additional information. If y is 24 when x is 8, find the constant of proportionality, that's what we're calling k, and the direct variation equation. And the direct variation equation is y equals kx. So what we need to know is what is the value of k, and that's it. Then y equals that number times x. That's it for our equation. So key to the code, y varies directly to x. That tells us we get to use the nice simple y equals kx formula. And then we're given some information. We know y equals 24 when x is equal to 8. So we can take that known information, plug it into our basic model here, giving us 24 for y equals that unknown k times x, and we know x is 8. So we can solve this for k. Nice simple equation. K is 3. So k, our constant of proportionality is 3, and with that we can write our equation. Y equals 3 times whatever x is. You're not going to find many simpler equations than these. Now, a little bit different type of problem, inverse variation. So we have direct variation and we have inverse variation. So direct variation is one variable gets larger, the other variable varies directly, so it gets larger also. When two variables are related inversely, as one variable increases, the other variable varies inversely and decreases. So one gets bigger, the other gets smaller. For that second job, those first examples we were looking at, the amount you earn per hour is the $100 you are being paid divided by the total number of hours it takes you to complete the job. And so our pay rate is 100 divided by h. So again, if we manage to complete the job in 1 hour, h is 1, and our pay rate is $100 per hour. If it takes us 100 hours to complete the job, our pay rate is $1. $100 divided by 100 hours is $1 per hour. So this is inverse variation. As one of the variables gets larger, as the number of hours to complete the job gets larger, our pay rate got smaller. And again, so y equals k over x. K is called the constant of variation, constant of proportionality, or the proportionality constant. You'll see all those different phrases popping up in different problems. So for an example, suppose y varies inversely to x. If y is 6 when x is 3, find the constant of variation, k, and the inverse variation equation. So since we're told y varies inversely to x, we know we're working with a y equals k divided by x model. We're given some additional information. We know y is 6 when x is equal to 3. And then we need to find our constant of proportionality, so we can take our known pieces of information, our known values for x and y equals k over x, and then we're replacing, we know that when y is 6, x has to be 3. Solving for k, multiply both sides by 3, we get 18 equals k. So our constant of proportionality for this relationship is 18. So when we write our final equation, the x and the y need to be letters, x and y, they're variables. But the proportionality constant is a constant, and we've just figured out what constant it is, and that gives us our equation y equals 18 over x. Once we have the equation, we could then use it to calculate values of y given values of x. So we can take that a step further, find y when x is 9. And then we can say y is 18 divided by, letting x be 9, y would have to be 2 when x is 9. Y got smaller as x got larger because of the inverse variation. Joint variation is direct variation using more variables. So something along the lines of y equals constant of proportionality k times a variable times another variable. And actually you've used this before. Do you remember the formula for the area of a triangle? Yes. Area of a triangle is 1/2 base times the height. This is an example of a joint variation problem. The area varies directly with both the base and the height. If the base of the triangle gets larger, the area of the triangle gets larger. If the height of the triangle gets larger, the area gets larger. So you've actually been doing joint variation problems all along and just didn't know it. Okay, this one's a little more complicated. So combined variation, putting everything together. So what it basically boils down to is you need to start off with y equal k, and then anything that's direct goes on top with the k, and any variables that vary inversely with y go down in the denominator. They get divided by the k. Okay, so if we have the maximum load a rectangular beam can support varies jointly, so code words there, varies jointly, as its width and the square of its height, but also inversely with its length. Don't even bother reading the second paragraph yet. Let's just focus on the initial information, set the problem up. We're not going to think about numbers yet. So what we're looking at is the load the beam can support. So let's use L for the load. And we need a constant of proportionality, so throw a K in there. So varies jointly. jointly, just directly with more than one variable. So with the width and the square of its height. So anything that varies directly or varies jointly goes up in the numerator with the k. So we're going to have k times the width and the square of the height, so h squared. But along with that, so this is all happening in one problem, the length of the load that the beam can support varies inversely with its length. So the longer the beam is, the less weight it can support. And so the length, which I'm going to denote with a little case l, goes down in the denominator. So as the length gets larger, the amount the load can bear gets smaller. But if the width of the beam gets thicker, it's a sturdier beam, the load increases. If the height of the beam, again making a bulkier beam, increases, then the load increases. So now that we've got the basic model set up, then we can start looking at the additional information, the specific numbers we're given. So if a beam is 1/3 foot wide, so let's just write that down, W equals 1/3. 1 foot high, so H equals 1 foot, and 10 feet long. This little l, the length, is 10 feet. It can support 3 tons. The load is 3. So just taking that information, we're going to put that information into our general model here, because what we're missing in our general model is k. We don't have the constant of variation yet. So putting in our known values, a little more room there, the load is 3 tons when a known constant of variation, the width is 1/3, the height is 1 squared, divided by the length, which is 10. Now we need to solve for k. So we do have a fractional equation, a rational equation here. I think what I'll do first thing to solve this is multiply both sides by 10. Again, as long as we're doing that to both sides of the equation, it's legit. So that gives us 30 equals, the 10's cancel here, k times 1/3 times 1 squared is 1, and 1/3 times 1 is still a third. So k times 1/3. And then to clean this up, I'm going to multiply by 3 this time, because 1/3 times 3 is 1, leave me just k over here on this side of the equation. And 3 times 30 is 90. So now I've got my constant of variation. And I can take that, put it into my general model here, and get a model for this beam. The load the beam can support is going to be 90 times the width of the beam in feet times the height squared divided by the total length of the beam. So after all that, we can now look at the last bit of information here. How much weight can a beam support? So what is the load on the beam if it's a foot wide, a 1/3 foot tall, and 9 feet long? So basically we've flipped it on its side and it's gotten a little shorter. Let's see what we've got now. I better copy this information down here. So let me leave a little room here. So we're looking for the load. That's unknown. The width is now 1 foot. The height is 1/3 of a foot. And the length is 9 feet. Okay, so putting this information in, the load is unknown. We know 90 is the proportionality constant. The width is 1. The height is 1/3, and in our formula, the height is squared, divided by the length of the beam, which is 9. So now we're going to evaluate. 90 times 1, of course, is 90. And 1/3 squared is 1/3 times 1/3, that would be 1/9. 1 times 1, 3 times 3. And my 9 down the denominator. 90 times 1/9 would be 10. So this load is going to be 1 1/9 tons. is how much weight the beam can support. Since we've now basically flipped it on its side, it's not quite as sturdy, even though it's gotten shorter.